we now look at the last case when we have complex eigenvalues. Let's look at this example. We have a system with the coefficient matrix over here. Rather interesting, 2, 3, and -3 and 2. You may ask, how do you know you're going to have complex roots? Soon we will see that. So in terms of matrix form, we have the derivative of xtyt is equal to this matrix times xtyt vector. So we get the coefficient matrix out, which is capital A. We have 2, 3 in the first row, -3, 2 in the second row. So we first find eigenvalues, and we set up the determinant. Matrix A minus lambda I. This I is the identity matrix, so lambda is simply on the diagonal. And then we have 2 minus lambda and 2 minus lambda on the main diagonal, and then 3 and -3 on the minor diagonal. And the determinant is supposed to be equal to 0 for eigenvalues. And then we multiply this determinant out. We have 2 minus lambda squared plus 9 is equal to 0. So move 9 to the right hand side, we get -9. So lambda minus 2 is the square root of -9, which is plus minus I, the imaginary unit, times 3. And added to both sides, we have eigenvalues equal to 2 plus minus I3. Now, next step, we need to find the corresponding eigenvector. We have two complex eigenvalues, but they are equivalent, so we just take one. And the eigenvalue we take is 2 plus I. And we want to find its corresponding eigenvector. And we set up the equation. The equation is the same matrix again, A minus lambda I, and multiplied by eigenvector should be equal to 0. Guaranteed, if we have found eigenvalue correctly, we should be able to find at least one non-zero eigenvector. And then we set up the vector in the component way, x1, x2, and plug in lambda. Lambda we use 2 plus I3 on the main diagonal. And then we simplify. We have this complex matrix, -I3, 3 in the first row, and -3, -I3 in the second row. We can use the usual method of reduced matrix, the coefficient matrix, to the echelon form. But we are pretty confident we have found the eigenvalue correctly, so we know we just need one equation to find the eigenvectors. We take the second one. So multiply the second row by this vector. We have -3 times x1 minus I3 times x2, which is equal to 0. Simplify, dividing both sides by -3, we have x1 plus I x2 is equal to 0. And we see that x2 is free, and then we solve x1 in terms of x2. So we have x1 is equal to -I x2. x2 is free, so we let x2 to be 1. And then we have this eigenvector. Then we have x1 is -I and x2 is 1. Next step, we need to find the real and imaginary parts of this eigenvector. So we just try to see what are the real and imaginary parts. For -I, the real part is 0, and the imaginary part is -1. For 1 is the real number, the real part is 1, the imaginary part is 0. Now we take the real part, which is 0, 1, and then the imaginary part is -1, 0. These two vectors. The real part is called V, and the imaginary part is called W. And we use these two vectors to find the general solution. And here is the formula we can develop from these two vectors to get the general solution. So this is the general solution formula, you can say. But please use exactly the same format, otherwise it's not going to be correct. So we have C1v plus C2w e to the alpha t cosine beta t. Alpha plus I beta is the eigenvalue, and then negative C1w plus C2v e to the alpha t and sine beta t. And then we plug in the values of v and w, then we have, let's just take another look. So C1 times v is 0, 1, so we have 0, C1. C2 times w, we have negative C2, 0, and then multiplied by this function over here. The same thing, negative C1 times w becomes C1, 0, this vector, and C2 times v becomes 0, C2. And then we have the second part. So put them together, that's what we have for the solution. Okay. And if you prefer, you can again write down these two components separately. The first one is for x of t. X of t is equal to, you can pull out the common factor e to the alpha t, then we have this nice looking solution. C1 sine beta t minus C2 cosine beta t, and y of t is equal to this. You may say, what does it mean? We have two arbitrary constants in the solution, so this is the general solution. Every solution of the differential equation is in this form, and we should be able to check if we take the derivatives and plug them in, then both these functions will satisfy the system of two equations that we started with. Okay, and that is how we solve for the general solution when we have complex eigenvalues.